Welcome back, everybody. So let's talk about the implementation of data cubes. So remember that this is one of the 5 shapes. And generally, when you want to implement a shape, you typically can do it in multiple ways. One of the ways is to try to save a bit of resources and save a bit of money. You just implement it on another shape. So you take a database system that supports another shape, and then you carefully design some mapping that allows you to use this other database system, and you nicely hide it from the user in such a way that to the end user, they see the shape that you want. We can use this approach with cubes. We can basically map cubes to tables and actually store the cubes as relational tables, as long as we add this lipstick around it that basically makes it look like cubes to the user. This approach is called rollup, relational rollup. Another approach for many data shapes is to not map it to any other shape. You just build the whole system from scratch, right? Yourself, natively. You can do it with cubes. That's called molap, right? So it's basically based on memory. You have your data cubes in memory, but with your own native data cube representation, and that's another way. Postgres is an example of table shape that is implemented natively, right? There is no other shape below it. Likewise, you can implement tables if you want on top of trees. So you could use a tree database management system that's known as a document store, and you could implement a relational database on top of a document store, right? You store them as trees, but you actually expose them as tables to the user. For whom does that make sense, right? You can do that with any shapes, either natively or on top of another shape. And I have this conjecture, I haven't fully formalized it, but basically all data shapes are equivalent to each other in the sense that you can always store data in one shape into another shape. It might be slow, but you can basically do it. You can store data in any shape. Today, I'm not going to talk about molap because that would be unnecessarily complicated. I will focus on rollup. Why? Because we've seen database relational tables the whole semester. So it's quite a natural thing to do. Plus, we are going to be using SQL. So it means that we compile kind of the cube queries, we compile them to SQL and execute some SQL codes on the tables. All right, so rollup. By the way, there's a third one that's called rollup. It's a hybrid form of the two that mixes relational tables and the native implementation. And of course, the vendors that use Essbase, Cognos, and so on, since they have relational database systems, it's a very natural thing for them to use rollup because they already have the implementation of the tables. The way you map a cube to a table, actually, I already mentioned it in the first hour. It's the fact table, right? This idea that you collapse the cube completely and then you pile up all the cells as a single large tower, and every one of these cells gives you one row, one record, one tuple in this table. Now, that's the rows. If you focus on the columns, what you see in a fact table is that all columns but one correspond to the dimensions. Right? See dimension 1, dimension 2, dimension 3, dimension 4, dimension 5. So that might be time, space, currency, salesperson, and so on. Except the last one. The last one has the value in there, right? So this is what you actually have in your cell, and all the other columns are the coordinates of the cell in the cube. So that's the fact table, and we do actually store it like this as a relational table in PostgreSQL, for example, or any other system. But that's not the only way. There is a slight variation of this. I think that's the next slide coming here. There is a slight variation of that, where instead of having only one value column, we have multiple such columns. It means that a cell doesn't have just one value, but it has multiple values. These are called measures. Concrete examples is profit, revenue, costs, expenses, and so on, right? So you might have for the same fiscal year, for the same quarter, for the same company, you might have revenues, profits, and so on. So in that case, you would put on the same row the profit, revenue, and expenses. They would share the same row, right? It's actually 3 cells technically, but they would share the same row. It's commonly done in practice, but what I want you to see is that it's actually equivalent. This and this is equivalent because you can actually map them to each other. It's called pivoting on pivoting. See how that works. If you had here revenue and profit in 2 separate columns, just reorganize it by piling them again as 4 plus 4, and then you put revenue and profit instead of being here, keep operating and disoperating. Instead of having them in the color header here, column header, you just put them here as in the measure column. Who sees that it's the same thing, that it's equivalent to do it one way or the other? Yep. So that's called pivoting and unpivoting. In fact, there's even extensions of SQL that allow you to do it in SQL, this pivoting and pivoting. So you can write a SQL query that does that in both directions. All right, so because of that, I'm not going to do it this way. I'm just going to do it that way. Much simpler. We have a single value column. The next thing is that typically when you have a facts table, it's like elephants, they live in tribes. So you have the fact table, but it also comes with satellite tables. And the satellite tables basically contain information on the dimensions that you have in here. For example, if you have, let's say, you imagine that you have a salesperson dimension with the identifier of a salesperson. In the sales table that concerns the salespeople, you might have the name, the address, the employee number, the salary, the department, and so on in that satellite table. Now, do you see how they relate the satellite tables to the facts table? With joins. You basically have a foreign key. These dimensions in the fact tables are actually foreign keys that point to the satellite tables to a primary key of some record in there. Who sees that? Right? And then that's called the star schema because it looks like a star. But some people who really love the normalization and really want it to the next level further normalize even the satellite table, and then you no longer call it a star schema. You call it very appropriate for the winter, a snowflake schema, right? Because it has even more satellite tables around the satellite tables. All right, so these are examples. Imagine that on the left, I have my facts table, and as a dimension, I have here the city, Zurich, Berlin, Interlaken. So imagine that's a foreign key that points to a primary key right here. That's my satellite table, and I have information about the city. Maybe the country, the population, like many things like here. And then if I push the normalization so far that I even have another foreign key pointing to another primary key here, pointing the country, the continent, and so on, that's basically my level 2 satellite table. So that's a snowflake schema. If I want a star schema, I just join these, right? If I join these, but then you will see that this is going to duplicate the countries, right? This is going to duplicate the continents and the countries. So Europe, and Asia. So that's basically in the third normal form, Boyce code normal form, but if you merge them back, you're no longer in the Boyce code normal form, right? So star schema or snowflake schema. Who is with me? Right, very good. So now, what people also do in practice is that they don't go to the snowflake schema, but they don't stop at the star schema, they even go all the way to join everything back into a single very big denormalized fact table. Right. So it means that even what was in the satellite tables, they just join it with the fact table and have here all of these dimensions even inside here the facts table. So it means that now for the same dimensions, you have multiple columns because these multiple columns came from the satellite table. That's an example where this is just one dimension here, where it's actually my cities, but I also joined and have the country and the continent. And you see that it's not in the Boyce code normal form. Why? Because there's a functional dependency from here to here and from here to here, but these are not super keys, right? So, and you see the duplication in here. So do you have a good intuition of that now? right? We've seen functional dependencies, normal forms, and so on. And so this is a denormalization. Okay. So in order to query cubes and tables, we have languages. For tables, you know it. It's SQL. We spent the entire semester on it. For cubes, there is also one. It's called MDX. That means multidimensional expressions. Don't worry. I'm not going to ask you to learn it and so on. I will show you maybe a few slides where you see it, but you won't have to learn it. What we are going to do, in fact, is just compile this to SQL, and we are going to focus on the SQL queries. It's a very good exercise to practice some SQL. So I'm going to use an example that looks like this, which is a cube with 3 dimensions. It's a cube of, let me see, 3 times 2 times 2. Do you see that? 3, 2, 2. 3 times 2, 6 times 2, 12, so that's 12 values. Okay? Everybody sees 3 times 2 times 2? Okay. Now, if I have my satellite tables, what you see in the first 3 columns are actually foreign keys that point to these satellite tables, right? So for the date, I might have the year and the quarter, Q1, Q2, Q3, Q4. For the customer, if I have the name, then I also have the country, the phone number, and so on. And then for the product, with its name, actually in real life, I wouldn't use the name, of course. I would use some reference number. Then I have the brand, and I have the price. Okay, so these are my satellite tables. Now, given these 4 tables, 3 satellite tables, 1 fact table, you could take the fact table and join it with the satellite tables, right? You know how to do a join, right? You can either use 2 tables in the from clause plus a where clause, or you can use the join clause, right? So here I kept it simple and just used 2 tables in the from clause plus a where clause with the join predicate. You know that this is efficient, by the way. Remember, PostgreSQL will know that this is a join, right? It will efficiently execute that. All right, so what I did here is that I joined my fact table right here via the date with the time, and I'm just extracting the year in here. It's a simple example, of course. In practice, you could use functions for doing that. I just want to demonstrate what it does. So here I join it with this other table, joining on the foreign key and the primary key. So that's the foreign key equal to the primary key. You could also do it with a natural join, of course. And then I put the year in there instead of the date. Okay, that's an example of what I could do. To simplify things, I'm going to forget about the satellite tables and just focus on the fact tables. So I'm going to assume that this is what we have. We are working with this table and only that table without anything else. I'm just going to use the years rather than the dates to simplify. Okay, so 3 times 2 times 2. Now, what we are about to do is write SQL queries that prepare the data that is necessary for displaying a nice view to the user. What has to be very clear is that SQL doesn't know the first thing about data cubes. SQL doesn't know about slicing and dicing. It doesn't know that we display some things on the rows and on the columns. It doesn't know anything of that. The only thing SQL can do is give you data in the form of tables. So what we are really doing here is just writing the SQL queries that give us the data we need to be cross-tabulated. And then the cross-tabulation, you need some more code in Python or whatever language you want, but this requires more work. This only gives us the values that go into the tabulation, the cross-tabulation. All right, so here, select year, brand, customer, quantity from sales. So that's the complete view. And if I want to do probably a slicing, yes, slicing. Well, that's something that you probably immediately saw, and that I mentioned, is that slicing translates in SQL with this mapping to a selection, a selection. And a selection in SQL is a where clause, right? So I just say where year is 2017, and that is going to give me the data corresponding to my sliced data cubes. Okay, so far it's easy, right? Everybody with me? Yeah, okay. So then I can slice further. Imagine that I add brand Samsung to my slicer. In the cross-tabulated view, that would all go to the top, right? As year 2017 brand Samsung, they would be in the slicer area of my cross-tabulation. Okay, but that gives us the data that would go in there. And of course, this would probably be based on some index, right? You could have an index that accelerates these filters. Okay. Now, what if we don't want to slice, but we want to roll up or aggregate? Imagine that I want to do what we did earlier of summing some values. I basically want to keep the year and the brand, but I want to sum over the customers. So you can see what we want to do in here, right? If I have 2017 Apple, I want it to go with 2017 Apple, right? So these two together, Peter and Mary, and I want the sum of that, 1 plus 5, right? Then I have 2017 Samsung, they're both here, and I want the sum of these two, 2 plus 3. How do you do it in SQL? That kind of things you use, what clause? A group by clause, exactly. So you say group by year and brand, so you group by this, and always, I told you in a group by, you always need to also put the same keys in the select clause, so year and brand also go here, and then anything else has to be aggregated. So the anything else here is the quantity, so we are summing over the quantity. Customer, we just drop, right? Because we aggregate on it, right? So customer goes away, and this is 1 plus 5, 2 plus 3, so 1 plus 5 is 6, 2 plus 3 is 5, and so on. Okay? So now I have the data that I'm going to put in a cross-tabulated view that corresponds to a roll-up. I rolled up on the customer, and now I have the whole salespeople team. Okay? I can roll up even more and also aggregate the brands, right? Then I only have the year left as a dicer, right? Did you see what's happening here? If I want to roll up, I need to remove from the group by, not add, remove. Everything that is in the group by is what you do not want to completely roll up. And when you want to completely roll up something, you just remove it from the group by. So if I want to also roll up the year, then I just completely, so then the group by completely goes away with just an aggregation in the select, and I have the total quantity, right? So this is just a succession of roll-ups. I roll up the customer, I roll up the brand, and I roll up the year. Okay? And then the opposite direction, that's drilling down, that's the opposite of roll-up, you drill down. If you want to drill down into the year and the brand, then you add them to the group by clause. Right? Remove to roll up, add to drill down. Okay, and of course, the sum is just an example. You don't have to be sum. It can be average, mean, max, count. There's many other functions. And the same goes in spreadsheet software. If you use the pivot table in spreadsheet software, you can, I think, click on the 3 little dots or right-click on your measure, and then you can select if you want to count sum, average, max, mean. You can select all of that. Okay. So this is just what I've done before, right? 1, 2, 3, 4. I just put them on my slide in here. Even one more. So here I have the dicing on year and brand. So customer is rolled up. Here I roll up everything but year. Here everything but brand, and here I have the total sum, right? Do you see that here, what I have is basically a grid because I have the subtotals. This is basically what would go in my cross tabulation. That would be the subtotals by year, and then the subtotals by brands, right? So maybe the subtotals would be these 3 at the bottom, and these 3 would be the subtotals on the right. And this is what at the bottom right, the grand total of everything, right? Which is both the sum of these and the sum of these. Still with me? Okay. But now, that sounds a bit inefficient because all of that data is what I need to populate my cross-tabulated view with these two subtotals and that grand total. But I have to run 4 SQL queries. Could we run just one SQL query to get all of that? And the answer is yes, we can. It requires a small extension that PostgreSQL actually has. The trick is to want to merge these to a single table. However, you see that if I merge them to a single table, it doesn't fulfill the relational integrity because they don't have the same columns. Here, there's 3 columns. Here, brand is missing. here year is missing, and here year and brand are missing. What can I do about it to forcibly add them back? If I would add, for example, in the second table, a column called brand, what would I put in there? Yes, that's it, the nulls. That's exactly the null approach. See? So you put here, I now also did the merge. These are my 6, maybe I need to bring back the green screen, see if the AI can do better than that with time. Here, the 6 go here. The 3 here go here, and indeed, as you correctly said, we put nulls in there, right? And by putting nulls, that's how I can add back the brand column, but I just put nulls. These 2 here come from here, right? And then null, null, that's my grand total. So you see that I was able to put it all in the same table. I just have my nulls here, and my nulls here, right? How do I do that query? Well, naively, I would say I take the union, right? I just have to add my null and null and null and null and so on to have the same columns, but I just take the union of these. That's still not very efficient. Can we do better than that? Yes, absolutely. Because there is this extension called grouping sets. We say group by grouping sets, year, brand, and nothing, that is in fact doing the union of these different group bys. So it's basically actually doing 4 times a group by and then taking the union. Who is with me? Right? So this is an extension of PostgreSQL. That's still good, not good enough, because imagine here it's just 2 dimensions, but what if you have 3 or more dimensions in here? It becomes complicated to list all the combinations in here. So you have one more shortcut that's called cube. Group by cube, year, brand, that is equivalent to doing that, right? It basically takes all combinations of what you put in there. And group by cube, year, brand, it works. It is in PostgreSQL. You can actually do it, and it gives you that. Who is with me? Then if you are with me, let's do a quick test. If I put n keys in there, group by cube with n keys, how many grouping sets do I get here? How many lines does that give me? Yes? 2 to the power of n, exactly. Because this is in fact the power set. These are all the subsets, strict or not, all the subsets of this. What are the subsets of that set? It's nothing, just here, just brand or year and brand. And you know that the total number of elements in the power set, the set of the subsets, is 2 to the power of n. Who already knew that? Okay. It's easy because it's combinatorics. When you want to count the number of ways you can select a subset of some set, in fact, selecting a subset just means for every element in my original set, either I take it or I don't take it. It's a yes or no. So for every one of the elements, it's a yes/no answer. So it's 2 possibilities, 2 possibilities, 2 possibilities, n times. So 2 times 2 times 2 times 2 to the power of n. So this is group by cube. As you can imagine, the reason it was added to PostgreSQL and many other systems is to support data cubes, obviously. So this is really having rollup in mind that they actually added this to the systems. And then in a single query, you can nicely build a relational table like this and create your cross-tabulated view, which is right here. That's the cross-tabulated view. So again, SQL can only give you that. You still need to write extra codes that produces the fancy visual, the cross-tabulation that you see here. All right, so now you know how to do it in SQL, group by cube. Just another example. So here, if you would add to the group by cube some where clause, you could also further filter, slice on Peter and so on. Who would be able to do that in SQL too? Great. You just add a where clause, right? All you need to do is add a where clause and then filter also on customer equals Peter. That's how you do it. You can mix the where and the group by. Okay. And here is just another example. Here I say periods 2017 and so on. Who could tell me quickly what the SQL query would look like for this one? the SQL that generates the data that goes in there. Yes? Mm-hmm. Yes? Customer, not everything, customer and brand. Yeah. So group by cube, customer and brand. So yes, absolutely. So that would be select, and that's not a star. I think it's select specifically. That would be select. Let me go back to the slide. This one. Select customer, brand, sum of quantity, where period is 2017, group by cube, customer, brand. Who sees that? Okay. It's exactly similar to before, and then we get the data that goes in there. Okay. All right. So that's group by cube. We need another one than group by cube. For a different use case, it's for the L shapes. How do we generate the data that goes in there where you have dimension hierarchies of more layers with more levels? We need something for that too. Because what's happening is that we want the values for every city, but we also want the aggregated values by country, and we also want the aggregated values by continents. If I have the same idea of merging with nulls, it looks like this. But do you see that this is not exactly the same structure as we had with group by cube? Because if I rewind and show you the group by cube that we had here, you see that the nulls that I have here, there's some here, and some here, right? So it's everywhere. But if you look now at the slide we have here, it's like a wave propagating from the right to the left. So we don't have everything in there. We don't have anything with only nulls in country or only nulls in continents. You only have the nulls propagating from the right to the left. So we need something else for that, right? Another example where we would need that is for quarters and years, if we divide the years into quarters. So now if we have the same idea of using a SQL query that does each one of the possible groupings, year, quarter, year, sales, but we don't have group by quarter here. Again, that's the difference with the previous one. Here, instead of being different dimensions, these are several levels within the same dimension. So that's the reason we just, from the right to the left, right? Quarter goes away, we have year, goes away, we have nothing, right? Then I can build these three tables, merge them, and again, I have my nulls, and so on. Take the union, then I have, again, the nulls that propagate from the right to the left. I can do it with a grouping set, and you see, again, this structure here, from the right to the left, year, quarter, year, nothing, but I don't have quarter in there. Do you see the difference? So if it's the same dimension, multiple levels, you have that structure where you just remove them from the right to the left. If you're looking at multiple dimensions that you want to display in a grid, then you have to look at the entire power set. The magic word for that is, tada, rollup, group by rollup. Right. So group by cube takes the entire power set. Group by rollup has a wave from the right to the left that basically removes the levels one by one. If I have n keys in my rollup, how many grouping sets do I generate? N plus 1, exactly. 2 to the power of n for group by cube, n plus 1 for rollup. And that is how, so this here, what you see here, is how you generate this view right here. Okay? Just group by rollup. So you see how important it is as a use case that the PostgreSQL engineers and even many database company engineers went all the way to extend the language with group by cube, group by grouping set, and so on. I mean, that's saying how important it is as a use case. All right, quickly about MDX, but again, very, very quickly. It means multidimensional expressions, MDX. Very common in computer science to use an X where it's actually EX, but it's cooler to have an X in there. It looks like this. So the first thing you notice is that it's not entirely dissimilar to SQL, right? You still recognize a select, a from, and so on. In fact, a lot of the query language is, even for graphs, we also have something that looks like this for trees and so on. So it's quite common to have this kind of structure. Now, the difference that you might see is, for example, the square brackets that basically represents your dimensions and domains and the members in the hierarchy. Plus, you have on columns and on rows. That is the dicing. SQL cannot do dicing. MDX can do dicing. So when you tell MDX on columns, on rows, it is actually producing this visual, the cross-tabulation visual. MDX can do that because it knows cubes. And then from sales, that's just the cube that you can have multiple cubes, of course, in a data warehouse, just like you can have multiple tables in a relational database. Okay, that's slicing. Slicing is with the where clause, which is a quite natural thing to do, given that also in SQL, when you compile it to SQL, that also lands in a where clause. So here I'm filtering and slicing on the MacBook Pros for Apple, and I'm putting on the rows all the profit, revenue, and so on. That's probably my balance sheet. And then I have the columns by location, right? Country by country, for example. Okay. So that's MDX, just so that you get an impression, but again, you don't have to learn it. I'm just telling you it's there. I think it comes from Microsoft Analysis Services, the MDX, and it has been adopted by some vendors as well. All right. And I want to finish on syntax. Syntax, we cover that a lot in Big Data for Engineers because this is needed for exchanging data over the internet. For example, if you want to download data sets from the internet, but also in the context of data lake, when you want to just drop data on a data lake, which is just a distributed file system. So we need syntax to actually save our data. Why do we need syntax in the context of data cubes? So why is it? The reason is that these data cubes are actually submitted to reporting authorities. For example, in the US, all the companies are required to submit their financial reports, so balance sheet, income statement, cash flow statement, statement of equity, and so on, to the SEC, the Securities and Exchange Commission. It's mandatory. And what's also mandatory, it's been mandatory now for 15 years, I think, is that not only are the companies required to file them, they are required to file them in the syntax I'm about to show you as data cubes. This syntax is called XBRL, Extensible Business Reporting Language. It's used all over the world now. It's used in the US. Japan has been doing it for a very long time. The EU has introduced it a couple of years ago. It's known as the European Single Electronic Format, I think ESEF. It's also going to be used for sustainability reports for the CO2 emissions and so on. Will also have to be filed in XBRL in the European Union. Switzerland also did a consultation with the Federal Council a while ago, again, probably about to be using that syntax as well. Why? Because that's the syntax for data cubes or this kind of representations. So briefly, let me show you. So first, of course, the end users are not seeing any syntax. What they see are the fancy views that I've shown you during 2 hours. This is an example, by the way. It's diced here with the measures. So that's an entire balance sheet. And it's diced here on the columns, the period. So this is end of 2019, end of 2018, right? That here is a report that was filed to the European Securities and Markets Authority in Paris. So this is for the European Union. Okay? So this is an example of balance sheet, and this was filed in XBRL. XBRL actually uses XML, which is the reason I'm not going to ask you to learn any of that. This is just a visual so that you see. If you're interested in XML and JSON, you can come back in Big Data for Engineers. But it basically uses a lot of standard technologies that were standardized by the W3C, just like HTML, HTTP, and so on. Don't be scared. Don't be scared. Don't run away. The end users don't actually see that. This is only what's hidden. So what is a modern way to file a report with XBRL? In fact, what you file is an HTML page that looks super fancy. Like this is really the super fancy and flashy, colorful end of year report. It almost looks like a PDF or a printed copy when you see it. You can open it in your browser, super fancy. But if you click on view source and look at what's actually in there, you will see that there is something more than HTML in there. There is also what we call tags. And the tags are basically put around the values. You can see, for example, there was a value here of 2,892,190. That's a value in there. It was probably one of these. Let's say that was this one, right? This is HTML, right? This is an HTML table. And in HTML, somewhere you have this. And what you do is you embed it into what's called a tag that says that this is the profit or loss. You see here, profit or loss, formatted with, these commas as a decimal. So this is just an indication of the way the number is formatted. And with some absolutely horribly looking string of characters that is just pointing to some context. And the context, which is somewhere else, is going to say, these are tangible assets for this company for this period. That's the context. And the unit here, which was also this horribly looking string of characters, is pointing to something that is probably euros. I assume that this is in euros, right? So all I want to say is this is an HTML page enhanced with tags around each one of the values in such a way that a computer can exactly know what each value means and can reconstruct this, because that's a human who sees that, right, if it's in HTML. But a computer can build the data cubes out of that. And once you have the data cube, you can even import it into a PostgreSQL database and so on, and continue to do it. So it's machine readable. That's basically what this electronic format gives us, all right? So that's the newer version where you just tag the data directly in the HTML files. There is an older version where you don't have any HTML, you just report the facts as a huge list of facts. So that's an example that's filed to the Securities and Exchange Commission in the US, where you have a number that are assets. The contexts, again, it's a horribly looking thing that points to something that looks like this. These are basically the dimensions. It's assets by Coca-Cola on December 31, 2011 in US dollars. So that's my context. The unit would be the US dollar part. And that's the number right here. And a filing is just a big file with several thousands of these that are all the values that you want to report to the SEC. Okay? The immediate benefit of that is that if there is a mistake in the report, something doesn't add up. For example, in the balance sheet, you have to make sure the equity and liabilities match the assets. If anything doesn't add up, it used to take weeks or months to basically get it back from the SEC saying, no, there's a mistake, please do it again. Now it takes seconds because the companies upload that electronic thing to the website. It's called EDGAR in the US. And if there is a validation mistake, they know immediately about it. Immediately, and then the company can fix it or do something about it. Well, in practice, they do not need to fix anything because there is software vendors that specialize in producing these reports, and of course, the software vendors validate themselves before you send it, right? So you know that it's actually going to make it through the validation, right? So this is an example, and again, that's what the context looks like. You have all this complex looking syntax, but that's just identifiers for the company, for the period, for the currency, and so on in there, all machine readable. And you just have this architecture with, it's very complex, actually very scary, scares a lot of people. But what's actually happening right now is the same thing as Excel or spreadsheet software. I don't know if you already did that, but has anybody ever renamed an Excel file as zip and unzipped it? You could do it, it would work. And if you unzip it, that's something that's going to scare you. It's really like huge hierarchy and so on, but it's all hidden. And so in XBRL, it's the same. All of that is actually going to be hidden. And all you have in the end is a file that looks like just XLSX, except that it's called XBRL something. And it works just like a spreadsheet file. All right. And Yeah, I don't need to scare you with all of these things, just further examples. On the SEC, the Securities and Exchange Commission, if you go there, you can actually view all the public filings. They did this beautiful work of the views. So these are artificial views. It's artificially reconstructed from the values that are in XBRL. And you see that it's a very nice technology that reconstructs all the data cubes and represents it like this, all machine readable. Okay, that was my last slide. So this is really an ongoing revolution that is going on now, because we can automate and save a lot of resources to get better quality. All right. Any questions so far on what we did? So if I wrap up, what did we do? We looked at another shape, data cubes. We looked at the logical model. We saw that the data cubes can actually be implemented on top of tables. We saw that it is actually commonly implemented on top of tables, that SQL was extended with syntax to deal with the logic necessary to compute grids and L-shape views with group by cube, group by rollup, group by grouping sets. And we saw that a concrete use case used in many countries around the world is syntax for filing data cubes like that. But this syntax exactly matches all the visuals that I've given you with the slicing and dicing cross-tabulated views. The best way to get practical experience is to take a CSV file that contains a fact table, open it in Excel or LibreOffice or OpenOffice or whatever you want, and then activate the pivot table and then drag and drop to make your view. That's really the best way to understand how it works. Very, very useful. I even use it in real life for many different purposes at work, right? Whenever it's very convenient to actually quickly aggregate data in specific ways. All right, so any questions? No questions? All right. So thank you very much for today. Next week, there will be no new material. I just tell you a bit about the database architecture, you know, as a concluding lecture. Then I'll wrap up. We'll have a big quiz game between the students and the TAs. Everybody on Zoom, please consider coming to the lecture hall. It's just for that last lecture, because if you win, you'll get the prize. And tell your friends to come. I mean, it's nice to just celebrate together the end of the semester. So this will be the final lecture next week. I'm gifting the Friday before Christmas to you. So I know many of you would like to go home, or so you can. We are slightly ahead of time, so this is a gift to you. And next week will be the final lecture. I will also talk about the exam a little bit. So thank you very much then, and see you next week.